we are interested in noise and why people are annoyed by certain sounds. So not necessarily loud sounds, but simply sounds that can be annoying and that it can drive you crazy. Well, and to bridge the gap, well, one man's noise may be another man's music. So while you might enjoy the sound of your motorcycle engine because you associate it with independence and freedom, your next door neighbor might consider it as unbearable noise because he associated it with inconsiderate behavior and crime. Well, it also holds the other way around. One man's music might be another man's noise. So whether you are enjoying some music might simply depend on which side of the wall you are. If you're sitting at the kitchen table with friends listening to music, you really enjoy this musical song. But if you're lying in the next apartment trying to sleep because you have an important meeting the next day, the exact same music might drive you crazy and really annoys you. The point I want to make here is that how we perceive sounds in general, not only music, is something very personal. And knowing about the sound does not tell you necessarily how someone will experience this sound. So we might indeed perceive the same sound very differently depending on the situation we are in, depending on our mood or the amount of hours we have slept. So the acoustic properties are much less relevant than what the person makes out of the sound. However, what a person makes of a sound can have severe consequences. So there are, besides hearing-related problems with noise, chronic low levels of noise can also have non-auditory negative health effects. So if your normal activities are disturbed, your sleep or communication situations, this can lead to cognitive and emotional responses and consequently lead to physiological stress reactions and consequently manifest in diseases. So it is a relevant topic. But I would like to ask here today in more general terms, what we would like to know is how do people actually perceive their everyday individual soundscape? So how many of the sounds that normally enter your ears throughout the day do you actually perceive, and what effects do these sounds have on you? The question is, how can we study this? Well, one way is we can simply ask people. But of course, that is something along an entire day, something very tedious and annoying. Just imagine that you're constantly interrupted by someone asking, did you perceive the last few minutes? At some point, it will change your perception of the world, because if you're constantly triggered towards giving an answer and assessment, you're going to pay attention differently to the world. So the alternative approach from asking people is to measure it objectively, and in a way that you don't have to ask people. And one tool we are using for this is EEG, because this provides us an approach to directly assess brain processes, which can tell us quite a lot about sound processing without having to have an overt reaction of the participant. And EEG is quite well suited to study auditory perception, and there are lots and lots of studies that used EEG to do so. But obviously, such a cap is not something you can do outside the lab. So it's not something you would consider to wear when you are having dinner with friends or being somewhere on the streets. For this, so the question is, how can we measure EEG in everyday life? For this, we have developed the C-grids. The C-grids is an electrode array, a very small one that goes around the ear. It just requires a bit of conductive gel, and then it's fixed to the skin with some sticker. And then you can wear it unobtrusively for an entire day. And this is something you would consider to wear in public. And we have conducted many studies that show us that we can actually record brain signals with these kinds of electrodes in the lab, but also beyond. The second part we have for our studies is the so-called necklace. So that's a device that integrates a neck speaker and a EEG amplifier. And this allows us now to record EEG while people move about in their everyday workspace. So it just goes around the neck, and then you are basically equipped to do an EEG recording, and people can behave quite freely, work at their desk, or even go to the Mensa or talk to other people. So Also, just short shout out to Daniel Hölle here. Most of the work I'm presenting today is based on his PhD thesis. So with this setup, we now have basically two options. So on the one hand, so the last element we need for this is a smartphone. And with this, we can take our experiments beyond the lab. So the smartphone records the EEG data, and we can also run experiments on the smartphone. And then the next speaker, for example, presents these sounds, and then we can run an experiment wherever we are in whatever situation we are in. The nice thing about this is that unlike with headphones, in our setups, the ears are not occluded, but we can still hear the normal acoustic scenery of a person without having to shut them down from what happens around them in the natural environment. So either we take the experiment beyond the lab or we make the world our experiment. So we can also use this setup to study how people perceive naturally occurring sounds. And for this, we have developed another smartphone app, and this smartphone app does a simple analysis of the acoustic scene, and then it extracts specific sound onset. So whenever there's a clear sound event, we get a trigger for our EEG signal, and based on this information, we can later on analyze the EEG, the brain response to these naturally occurring sounds. So how can we use now EEG to understand how people perceive sounds in everyday life? So first I will talk about our approach of taking the experiment beyond the lab. We run a study where we present people with a sequence of sounds. We always present double beep sounds, always beep beep, then there's a break of 8 to 9 seconds, and then the next pair of beeps occurs. And we now want to know in everyday life how people perceive these sounds while they are working on a normal everyday workspace. But in order to be able to interpret these results, we first characterize the people in the lab so that we have some reference signal, and then we can see how that relates to everyday situations. So we ask people in controlled lab experiments to listen to these beep sounds under different conditions. First, we instruct them for 15 minutes to simply sit there and passive listen to these sounds without any instruction. Then next, we give them a secondary task, just like you would have in everyday life. We ask them to read a newspaper article while they still listen to these sounds and they don't have any task concerning the beep sounds. The next part is that we play a text to them, so a newspaper is read to them, and again, they have to listen to these sounds. And finally, we have a condition where they have to pay explicit attention to the sound streams. And you might have noticed that in my sequence up there are some deviant sounds. So sometimes the second tone is a bit different. And in the active conditions, participants have to pay attention to these pitch deviant sounds, and they have to count them. So whenever the second sound of a sound pair is different, they have to count, okay, there's a deviant sound. So in this task, they actively have to engage into the sound stream, and we hope that we basically cover then different listening situations that would also occur in everyday life. You either listen passively or you listen actively to something. And so we can use those as reference signals. So let's see what we can learn from this lab-based study first. And I'm going to present you now the result of 11 participants that have done these tasks in the lab. And what you can see here, where's my, yes, my laser pointer. Yes, what we can see here is now the ERP, the evoked brain response to these sounds. And you can see here what you normally observe. So you can see here to the first tone, a clear result, a so-called N100 following 100 milliseconds after the first beep tone. That's a well-described effect. And you can see that the response to the second tone, so here the second tone occurs, and you would expect a similar response as the first one, but you can see that the second response is way smaller. So despite the fact that it's the same tone presented twice, the fact that the second tone occurs after the first tone, so you're already accustomed to the tone, the brain adapts to this, you get a much smaller response. So this shows us that the setup basically works and that we can learn something about the sound environment. Next, we look at the response to the reading condition, and there you can find a very similar pattern. Again, you get a clear response to the first sound and a much weaker one to the second one. Overall, the signal is a bit smaller, likely because you are shifting your attention differently. You're not, you're engaged in something else. And then in the third condition, the listening condition, you see an even smaller response, very likely due to the fact that sometimes it might happen that the tones we are presenting experimentally are masked by the audiobook and you simply hear less, and also that your auditory attention is directed in a different way. So based on these results, we can basically see two things about auditory perception. First, auditory perception, or the brain response to auditory stimuli, depends on the direct acoustic context, so whether a tone is presented first or second. And it also depends on the larger context. So it depends on what we do and what else is going on. So now look at the, let us look at the last condition. In that case, we ask people to actively pay attention to the sounds. And they had to respond to some of these sounds. And in that case, we get a very different response. Now you can see a very large response to the second sound as well as to the first sound. And keep in mind that the sounds did not change whatsoever. So it's exactly the same sound material. The only thing that changed was now the task of the participant and the intention toward the sound changes. Because in order to do the task, people had to pay attention to the second sound. And even though that what I'm showing here is always the response to the same sound, so not the sound they had to respond to, they still react stronger to the second sound because it could potentially make a difference. So depending on your intention, the brain response is different to exactly the same stimulus material. So the interesting question now, of course, is how do people perceive these sounds in everyday life? Is it the case that they listen to those sounds more like we've seen in the active condition or more like in the passive condition? And for this, we did the exact same paradigm again while people were wearing this device here and while they were working on the lab for 3 hours. And we presented this tone sequence from time to time. And in between those sequences, there were always 1.5 to 5.5 minutes break. And then we continued that 36 times over the day of, over the course of the morning while they were working and while they went to the cafeteria. So the question is now, what is the default mode of people listening? Do they listen more actively or more passively to these experimental sounds? And when we look at these results, we again see a very clear ERP response, looks similar to what we have seen before. So that's nice because it shows that we can actually record brain activity in everyday situations with this kind of setup. The question now is, how does that relate to our reference recording? And when we compare it to the passive and active listening condition, we see that on average, this response resembles more the passive condition than the active condition, which is not really surprising because people very likely didn't interact actively with this task. But it's very nice that we can see that and that we can use this approach we are developing here to compare it to different listening modes. So the results are interesting in itself because it shows what we can do with this approach. But what I find way more interesting is how does the brain respond to actual sounds in our environment? So how do we react to naturally occurring sounds and not only to these experimental sounds? So can we use EEG to understand how people perceive sounds in everyday life? Now we take the step and make the world our experiment. And as I've said in the beginning, in this study, we did not only present the experimental stimuli, but we also recorded all the sounds that occurred naturally around the participants. We identified onsets of events, and then later on, we can compute the neural response to those naturally occurring sounds. And I'm going to show you now the brain response to these naturally occurring loud sounds, very distinct sounds. And unfortunately, we don't see much in this case. So you can see here a wiggly line but it does not show the same pattern as we have before. So for comparison, this is the response to the experimental presented sounds. And on the other side, we have the response to the naturally occurring sounds. Well, that was kind of a disappointment because we thought we did all this development of our hardware in order to do exactly this, to study naturally occurring sounds. So what happens here? Why don't we see here a response? One possible explanation could be that the naturally occurring sounds are too diverse and too different so that we don't get any clear responses. However, when we did another study beforehand where we recorded natural soundscapes, and then we played those soundscapes back to the participants in the lab. So people were sitting in the lab and listening to naturally occurring soundscape. We again extracted onsets and we computed the ERP. And in that case, we also get a very clear ERP response. So in principle, it should work. So why don't we see anything in this frisk condition? What's going on here? Well, we are just starting to dig deeper into this topic, but I think what we see here is the reason why we need to study auditory perception in the wild, because it's different from what we can do in the lab and what we normally see in the lab. So in how far does the frisk condition differ from those other two conditions? Well, the frisk condition is the only one where we have the sounds in a plausible context. So many of the sounds in everyday life are highly expected. They are potentially self-generated, they are anticipated, they make sense. They are attached to objects, you know that they are occurring. You have somehow, you have some degree of context. For the experimental sounds presented here, they just, when we present them with the necklace, they just happen from time to time randomly, they pop up without any clear indication where they are coming from or why they are there. So it's very surprising. And the same is true when we use natural sounds and present them in the lab. Also there, we don't have a clear idea where these sounds are coming from. You just hear random sounds, but you don't have, at least for this paradigm here, any visual cues. The sounds don't have any meaning, no origin, and therefore they are different to anything that we experience in the lab. So the real world is different than anything that we can develop or create in the lab. And we are not passive listeners. We are actively involved in our acoustic environment. We move around, we create sounds ourselves. We are not that often surprised by sounds if we are in specific context. So to conclude, I've shown you that we can record EEG in everyday life situations and that it's possible to do this with a fairly unconspicuous setup. We can relate the ongoing EEG to auditory events as they occur either from an experimental device. But we also see that the brain response to experimental stimuli outside the lab and the brain response to natural sounds in the lab may be different from the brain response to natural sounds outside of the lab. Oops, that's the wrong way. Yes, thank you very much.